Quadratic expressions are not unfamiliar to us. When solving, a lot of time is spent in the last, well, and I guess in the first section of this algebra class and in the last algebra class that you had before this. Quadratic expression in the variable x, an expression that can be written in the form ax squared plus bx plus c. It's got to have an x squared term, otherwise it's not quadratic, it's linear. It may or may not have an x term, may or may not have a constant term, but we insist that a not be 0 to ensure the presence of an x squared term. If we toss in an equal sign and declare it to equal 0 or some other perhaps quadratic expression, then we have ourselves a quadratic equation, which we can solve through various different methods. We've looked at the method of factoring. We've looked at the square root method if the x term happens to be missing. If it can't be factored and there is an unsightly x term, we can use the quadratic formula. If it's particularly nice, though, we could maybe use the method of completing the square. 4 different methods we've looked at for solving quadratic equations. But there'll be an equal sign, and there'll also be an x squared term. If we define a function by saying f of x equals a quadratic expression, ax squared plus bx plus c, we have ourselves a quadratic function. Again, a is not allowed to be 0, so there must be an x squared term. May or may not be an x term, may or may not be a constant term, but that will define a quadratic function. Is the thing still stuck? Well, at least let me close the window. I just have to be careful not to click on it. I don't know how I'll be able to avoid that. There we go. Fun fact about quadratic functions. It fits the definition of quadratic function if it's written in the form f of x equals ax squared plus bx plus c. If it's written in that form, it can also be, through a couple different methods that we'll look at, written in this potentially more useful form, a times x minus h quantity squared plus k. We might call this the vertex form. I don't know if the textbook really calls it that, but it displays the vertex of the quadratic function for us, so it'd be a good name for it. If we look at the graph, the lowest point on that graph is called the vertex, and its coordinates are hk, according to the way it's defined here. If it opens downward, the highest point is hk, according to the way it's defined there. And how do we know, just by looking at the expression, whether it opens up or down? If the coefficient of x squared is positive, it opens upward. If the coefficient of x squared is negative, it opens downward. And we should be able to see this in example 1a and example 1b, both how we get the vertex and how we notice that it opens downward just by using some transformations from section 2.7. So the a part, graph each quadratic function using transformations. So if we start with y equals x squared, one transformation we might do is, what happens when you multiply the right-hand side by 2? It's going to look like a horizontal shrinking. Technically, you could think of it as a horizontal shrinking by a factor of 1 over the square root of 2, but I'd prefer not to think of it like that. I'd rather think of it as a vertical stretch or stretching by a factor of 2, because if you look at y equals x squared, doesn't it kind of look like a horizontal shrinking by a factor of 1 over the square root of 2? It sort of does, but let's instead think of it as a vertical stretch. Point right here, I guess right here, gets stretched vertically twice as far from the x-axis as it originally was. So I'm going to dispense with the original y equals x squared and just focus on our attention on y equals 2x squared. It's going to be skinnier, steeper than the original. Y equals 2x squared. What if we substitute x minus 3 for x. It'll go 3 units which way? Three to the right. 3 to the right. Graph it. And we see it go 3 to the right. Finally, subtract 8. Y equals 2 times x minus 3 quantity squared. Then y equals 2 times x minus 3 quantity squared minus 8. We've subtracted 8 from the right-hand side. So it will shift the graph 8 units. Which way? 8 units down. The thing to keep in mind is what happens to the vertex under each of these transformations. In the original y equals x squared starts at the origin. So let's see, the vertex here is the origin. The vertex here got shifted 3 to the right, and the vertex here got shifted 8 down. So 3 to the right and 8 down, so we can look at these numbers and tell that the x-coordinate of the vertex is positive 3, and the y-coordinate of the vertex is actually negative 8. On the inside, it's the opposite of the sign, because there is a minus in front of the h. So positive 3 for the x-coordinate of the vertex, negative 8 for the y-coordinate of the vertex. And you can see the graph there, the lowest point on that graph is 3, negative 8. The b part, there's no stretching or shrinking going on, but there is a reflection. Let's go ahead and get that out of the way first. If we multiply the right-hand side by negative 1, I guess I've got to go back all the way to x squared. Maybe change that to a negative. Change that to a negative and what? Going 6 to the right. And change that to a negative 6 to the right, and then 9 up. But, lest I forget to holler spoiler alert, let me deselect those. So this is the first two, y equals x squared and y equals negative x squared. You can see the x-axis reflection. Vertex stays put, 0, 0 in each one. But then, what happens to the vertex when we shift 6 units to the right? Well, I would guess it gets shifted 6 units to the right. So if we have, there's the vertex, the origin, and then y equals negative x squared to y equals the negative of x minus 6 quantity squared. The vertex now is the 0.60. And then when we add 9, what happens to that vertex? It's 9 up. So it goes from the 0.60 to the 0.69. Y equals negative x minus 6 quantity squared. Y equals negative x minus 6 quantity squared plus 9. The vertex is the 0.69. So h equals 6. K equals 9. We'd like to be able to look at this form and immediately tell, the x-coordinate of the vertex is this, the y-coordinate of the vertex is this. Those are going to be some important, or an important feature of the graph of this quadratic function. Sometimes, though, the function is not handed to us in that form. It looks more like this. And we want to put it in the form f of x equals a times x minus h quantity squared plus k. One way to do that is by completing the square. Now, if we have a quick review of completing the square, if we have x squared plus 10x, what's the magic number we can add to that to make that a perfect square trinomial? 25. Half of 10 is 5. Square the 5, get 25. That gives us x plus 5 quantity squared. If it's like x squared minus, yeah, it's 14x. What's the magic number we can add to that to make that a perfect square trinomial? 49. Doesn't matter whether the 14 is positive or negative. Half of that would be negative in this case, but we square it and we get something positive. I guess it does matter there because it'd be x minus 7 quantity squared instead of x plus 7 quantity squared. Notice, in both these cases, there is a positive 1 in front of the x squared. If we want to be able to take the coefficient of x, cut it in half, square it, add it, and have that give us a perfect square trinomial, the coefficient of x squared needs to be 1. In this case, it's negative 1. So if I want to complete the square, I have to remedy that by factoring out a negative 1 or a negative sign, as I've done here, factoring out a negative. Notice I did not factor the negative out of the negative 27 because the negative 27 would just be in the way. So I'm leaving the minus 27 out of the parentheses. It wouldn't be the end of the world to put it inside as a plus 27. It's just in the way. So I'm leaving it outside the parentheses, and we'll deal with that later. F of x equals the negative of x squared minus 12x. Okay. Plus what?
36.
Well, half of negative 12 is negative 6. Square that, get 36. So plus 36. Now, the simplest thing to do in this case, I think it takes an extra step, to see that we're really not messing up this function, we've written a plus 36 if immediately thereafter we write a minus 36. And just are confident that we've added whatever 36 minus 36 is. We know we won't have changed the value of this function. But if we want to save a step, we could ask ourselves this question. By writing the plus 36, the red plus 36 there, we've actually changed the value of this function by how much?
36.
Well, careful.
6.
Well, technically. Yeah. Basically, what's the if I simplified this, cleared the parentheses, it actually would differ from the original by how much?
Negative 9.
Well,
Because you move the 27 over to the right side.
well, what's the same about these is they both have a minus 27. So the minus 27 wouldn't be any difference between them. The only difference is what's in red, or maybe what's in red. The difference is negative 36. It's tricky, but when we write the plus red 36 in there, inside the parentheses, I've actually subtracted 36 from the original. I've got the negative out in front. If we were to clear the parentheses, this function would be 36 less than the original function. 36 less. So to compensate for that, what I would want to do is put a plus 36 on the outside. Now that's crazy tricky, and I'm maybe not suggesting that you try this at home. But I felt the need to mention it here in class. The safer course of action is just to put a minus 36 right next to it. That way it's guaranteed that you're adding 0. You're changing the way the expression looks, but you're being sure not to change its value. Now, what is the value of this thing? It's negative x squared minus 12x plus 36. Okay, the minus 36 is in the way. It's not part of that perfect square trinomial, so we got to get it out of the parentheses. When we do that, what happens?
It becomes plus 36.
It becomes plus 36. So there we go. I think we're ready to write the final answer here. F of x equals the negative of x minus 6 inside there, and then plus 9 on the outside. So that puts it in the form that we want. A equals -1, h equals 6, k equals 9. So it opens downward, and its highest point is the 0.69. It's that. Which one? Not that one. Not that one. Not that one. It's that one. Opens downward. Its highest point is the 0.69. Didn't ask for the vertex, but once it's in this form, did it ask for the vertex? Nope. But once it's in that form, we can do that. Notice the B part quickly. I don't want to reproduce that for you. It's there for your viewing pleasure. But notice what I did there. See if we can follow this. Where there was a minus before, there's a 2 now. 2x squared. It needs to be 1x squared if we're going to be able to complete the square. So we factor out the 2. We factor out the 2 and leave the plus 10 away from things because it's going to be in the way. Leave it outside the parentheses. There's an x squared minus 6x inside. Easy enough to come up with a plus 9. Half of -6 and -3. Square the -3, get 9. So x squared minus 6x plus 9. All right, I kept this on the nice and easy side because plus 9 minus 9, basically right there, we're adding 0 to the value of the function to make sure we don't change its value. But we change the way it looks. What happens to the minus 9 when it comes outside the parentheses? Minus 18. The plus 9 actually added 18 to it, so we had to compensate for that by subtracting 18, but it's done. And then when you simplify what's on the end there, there's a minus 8. So a equals 2, h equals 3, k equals -8. It opens upward. It's a little skinnier than y equals x squared. And its vertex, its vertex is the 0.3, -8. Now, if I felt like, I guess if we had reached this point in the semester and it's still like the first week of March, and I'm wondering what we're going to do with all the extra time we're going to have, I would go through, take f of x equals ax squared plus bx plus c, complete the square, and actually show that the vertex in that case has an x-coordinate of -b over 2a. I think I'm going to skip the details though, and just give you the punchline. If you begin with f of x equals ax squared plus bx plus c, and you complete the square, what would have to happen? You factor out the a, and you're staring at x squared plus b over a times x. And you have the b over a times x, and you cut the b over a in half. You get b over 2a. And then you square that and add it and then subtract it, and then, well, again, I'm going to spare you the details, but what happens is what you get is f of x equals a times x minus -b over 2a, quantity squared, plus a k value. And the k value, you could express that in terms of a, b, and c. It's really not a big deal, because what we'll do to find the vertex is evaluate the function at -b over 2a. So the vertex formula is given here. -b over 2a, f of -b over 2a. We can use this to find the highest point on the graph or the lowest point on the graph, and if it's a quadratic function, we can find the maximum value of the function by looking at the y-coordinate of the vertex, or maybe the minimum value of the function by looking at the y-coordinate of the vertex. That turns out to be important in some applications. Oh, I did it again. Good grief. All right, got it back. Example 4. Oh, what can we do with 4 minutes and change? We can find some of this. It's been a while since we found x and y intercepts. A quick review of how to find the x-intercepts of a function. Or maybe for the very first time. We found x and y-intercepts of graphs of equations. To find the x-intercept of an equation, we generally substitute 0 for what? For y. Substitute 0 for y. Since we really don't have a y here, basically it's y equals 4x squared minus 24x plus 27. We're substituting 0 for f of x. We want to solve the equation f of x equals 0. So we want to solve 4x squared minus 24x plus 27 equals 0. And it's going to take us the rest of this 3 minutes to factor this thing. I don't know. If I give you a hint, suppose it's 2x minus something and 2x minus something else. I mean, there's that possibility. The other possibility, it's x minus something and 4x minus something else. But let's imagine we've already checked that one. Any thoughts as to what these numbers ought to be? Factors of 27, I guess. Not that many things to choose from if it actually can be factored. What would we have to check first?
9 and 3.
I would think 9 and 3. If we FOIL, we get minus 6x. We get minus 18x. I guess I'm not foiling, I'm just oying. Because we feel good about the f and the l. Minus 6x minus 18x is minus 24x. So it gives us the middle term. We're good with the 27. We're good with the 4x squared. So 2x minus 9 equals 0. Or 2x minus 3 equals 0. X equals 4.5. Or x equals 1.5. So the points to plot are 4.5 comma 0 and 1.5 comma 0. Y-intercept is easy, as it usually is for functions. F of 0. To find the y-intercept, we substitute 0 for x. For a function, it's f of 0. Put the x inside the parentheses, f of 0. And for a polynomial function, in this ax squared plus bx plus c form, quadratic function I should say, it's just the constant term. It's 27. So 0, 27. Can I find the vertex in like 1.5 minutes? What do you think?
Yes.
I think it can be done. A equals 4, B equals negative 24, C equals 27. We could complete the square, but let's try out this vertex formula. H equals negative B over 2A. That's the opposite of negative 24 over 2 times 4, which is 24 over 8. It tells us the x-coordinate of the vertex is 3. If we have the x-coordinate of a point on the graph of a function, how do we find the y-coordinate? Substitute it in. F of 3 is going to be 4 times 3 squared minus 24 times 3 plus 27. That's 4 times 9 minus 72 plus 27. It's 36 minus 72 plus 27. It's negative 36 plus 27. So the vertex is 3, negative 9. No time to graph this. We're out of time. But that's the idea. I believe we finished up with example 4 last time. Finding the intercepts and vertex of this particular quadratic function, and we found just about everything that we needed. Use the, well, to find the x-intercepts of this function for any function, basically you set the expression that's used to define the function equal to 0, solve that for x, and we did. We were able to factor that quadratic expression. We got 4.5 and 1.5 for the x-intercepts. For the y-intercept for any function, just evaluate at 0. Substitute 0 for x. and we got the point 3, negative 9. Sorry, we got 0, 27. When we found the vertex, we used the vertex formula. Negative b over 2a gives the x-coordinate of the vertex, and if we evaluate the function there, we get the y-coordinate. So we have some key features of the graph. Let's go ahead and plot them and look at a couple other key features and then try to answer some questions about what's going on with this graph. So let's go 1, 2, 3, 4, 5, 6. Since the x-coordinate of the vertex is 3, I'll go out about twice that far. The y-intercept has a y-coordinate of 27. So I think if we go up and do about 30 in multiples of 10, it would fit nicely on the graph. So maybe 10, 20, 30, and negative 10 down here. Also, in deciding on a scale for the y-axis, it's probably a good idea to take the vertex into account. We definitely want to include the vertex on the graph, but it does just barely fit on this scale. 3, negative 9 is going to be about right here. The x and y intercepts are at 4.5 and 1.5. The y-intercept at 0, 27. We toss in one additional point you can get for free. Actually, before that, the axis of symmetry. These quadratic functions are always going to have a vertical axis of symmetry. So the equation of the vertical line is of the form x equals a number. All we need is the x-coordinate of the axis of symmetry, 3 in this case, and if we draw a vertical line through the vertex, there's our axis of symmetry. So basically x equals negative b over 2a is going to give us that coordinate. Once we have the axis of symmetry, there is one other point that we get for free, basically. It's the image of the y-intercept about the axis of symmetry. If the graph has x-intercepts like this one does, they will always be images of each other about the axis of symmetry. Each one of those points is 1.5 units away from the x-axis. One to the left, the other one to the right. The y-intercept is where it is. It's always a distance of whatever the absolute value of the x-coordinate of the vertex is. So if we go that distance on the other side of the axis of symmetry, it's 3 to the left where it is. If we go 3 to the right, we get the point 627. And I say we get that for free just by observing that it's 3 units to the right of the vertex with the 3 units to the right of, the axis of symmetry with a y-coordinate of 27. That's a little bit easier than taking 6 and plugging it into x in the original expression that's given there. So it's less expensive as far as the labor to come up with the 27 is involved. Then connect the dots, and we have hopefully a decent graph of this quadratic function. Something kind of like that. And some questions about it. We looked at properties of functions several sections ago, but once we have the graph and some basic features here, we can answer questions like, what is the domain? What's the domain of this function? Are there any bad values of x that don't work? None. No. There are no x's in the denominator that could give us 0 in the denominator. There are no radicals that could cause us to have to take the square root of a negative number. So all the x's are good. No x's are bad. The graph goes all the way to the left, all the way to the right. No holes, discontinuities, gaps, anything like that. So the domain is all real numbers. What is the range? It's helpful to have the range. It's helpful to have the graph. When looking for the range, we ask ourselves questions like, how low does the graph go? How low does this graph go? -9. And it goes that far. It's a bracket there at -9. How high does it go? It goes all the way up, so positive infinity. There we go. -9 to positive infinity. What is the minimum value. It's the least number in the range. It is -9. There are a lot of different numbers that we can substitute for x. For every number we substitute for x, we get something greater than or equal to 9. Sorry, greater than or equal to -9. If we substitute 3 for x, we get -9. And that is the least number in the range, so it's the minimum value. What is the maximum value? Yeah, basically we just say none. It goes all the way up. It's unbounded above, so there is no maximum value for this quadratic function. In general, when we look at these quadratic functions, either the graph will be a parabola that opens up, or a parabola that opens downward. So they'll have a lowest point or a highest point. In either case, the coordinates of that point are going to be negative b over 2a, f of negative b over 2a. If it opens upward, it has a lowest point, so f of b over 2a is the minimum. If it opens downward, it has a highest point, so f of negative b over 2a is the maximum value of that function. How do we tell whether it opens up or down? We look at the A. If A is positive, then no x-axis reflection has taken place in transforming the graph to get to the graph. So A is positive in that case, A is negative in that case. I just want to move the thing around. Actually, I'm going to skip an example. I'm going to skip example 5 and finding the maximum value or minimum value of a quadratic function, because this application really kind of covers that topic. The rectangle that's indicated here is that of a rectangular pen, perhaps for enclosing farm animals or whatever. This is the top view. A rectangular pen with one interior partition or partitioning wall right here, positioned so it's parallel to one pair of exterior sides, as opposed to maybe something like that. I suppose you could put the wall right there, but that's not what's called for in this case. It's parallel to one pair of exterior sides. Is going to be formed using 900 feet of fencing material. That's the plan. That's what's budgeted for. That's how many feet of fencing material. And the fencing material is got to go all the way around the outside. And we're going to use the same type of fencing material for the partitioning wall. So add up all the lengths of the fencing material. It's 900 feet. Express the total area enclosed by the fence as a function of x, the width. So we'll pick the dimension, x, and call that the width of the pen, and then find the maximum area that can be enclosed by the fence and the dimensions of the fence that produce this maximum area. I think first thing to do is observe that if we build it differently, build it like this, as opposed maybe to building it like this, we could use the same amount of fencing material, add up all the sides and the interior partitioning wall, and it adds up to 900 feet. but it might enclose a slightly different amount of area depending on the dimensions. So let's do just a couple quick calculations. Suppose x equals 100 feet. Let's see how long it can be so that the total amount of fencing material is 900 feet, and then area equals what for a rectangle? What's the formula? How do we find the area of a rectangle? Is it pi r squared? What's the formula for the area of a rectangle? It is length times width. So let's find how long this thing is and then figure out the area. So 100 there and 100 there. That's 300. We've got 600 left. And that 600 has to cover, well, the way I visualize this, well, the two longer sides. So if we've got a total of 600 feet of fencing material left, we need to cut that in half. So 300 from there to there, and 300 from there to there. So, how much area for this fence? 100 feet times 300 feet, going with width times length actually, is 30,000 square feet. Let me warm up I guess the calculator's already warm. Yeah, that's good, in case I need that. Suppose we don't want to make that wide, and we have an area that's longer than it is wide that we want to put it in. Still want to go ahead and use up to 900 feet of fencing material. Instead of 100, let's make this 50. And let's make this 50. And let's make this 50. 50 and 50 and 50 is 150. Okay, maybe calculator time. If we had 900 and we used 150, that's 700 feet of fencing material that we have left. And so we can cut that in half, put half of it for one side length and half of it for the other. What is half of 750? About 375. Well, the way I've drawn it, looks like I'm using maybe more than half. That looks like about the 50 that I've got right there. I suppose I could make it just a little longer than that, but I mean just a little wider than that. But if I want to draw it to scale, that's probably a good idea. Help us visualize this. If I make it 50 according to what I've drawn there, then I can only go 375. So I would say it's about 50 by 375 on the same scale. So 50, 50, 50. Worried about this one now. Just want the visual to work here. Almost. I just want to look about half. There we go. Something like that. 50, 50, 50. 375 from there to there. 375 from there to there. Regardless of the picture, I hope I'm close there. The area of this one is 50 feet times 375 feet, which is how many square feet? Really looking for the times button there. There it is. 375, 18,750. I don't know if the discrepancy in area is apparent from my diagram there. I'm thinking it's maybe not that clear. Maybe the bottom fence drew a little bit too wide compared to the other one. But it's less area, 18,750 square feet, a good bit less. So if we're thinking about how to make the dimensions, it makes a difference how wide it is. In this case, if we start at 50 and then make it wider, it would appear that we can enclose more area. Now if we make it too wide, if we make it 200, say 200, and then 200, and then 200, like that, how long can we make it? That's 600, and there's 300 left, so I'm thinking just 150, and 150, how much area would that enclose? $30,000. All right, so maybe that would work about as well as our 100 by 300, but it doesn't look like it's necessarily going to just keep going up, up, and up, up. If we go even wider there, I think it's going to be more difficult to enclose that area. So what we'd like to do is express the area of this as a function of x. Let x be the width, and for the moment, call this other dimension y. The area of a rectangle is the width times the length, or the length times the width, whichever you prefer. X times y in this case. But we can write an equation involving x and y because there's this constraint. There are only 900 feet of fencing material that we can use. So x plus x plus x plus y equals 900 feet of fencing material. Add up all the dimensions there, the walls that we have to fence there, that's what it's going to be. So 3x plus 2y equals 900. What we want, and we've seen in 3 examples that if we can figure out what x is, or if someone gives us what x is, we can figure out what y is. So we ought to be able to express y in terms of x, and we can pretty easily. We subtract 3x from both sides, 2y equals negative 3x plus 900. And if we divide both sides by 2, y equals negative 3 halves x plus 450. See if that makes sense. If x equals 200, 200, 200, does that mean y has to equal 150? 150? Well, negative 3 halves times 200 is negative... Wait. Half of 900 is 450. Negative 3 halves times 200 is negative 300. Negative 300 plus 450 gives us the 150 for the y value. So if we tell it how wide it should be, we can compute how long it should be. So the area equals x times negative 3 halves x plus 450. We can even write it as an area function now, a function of x. As we put in x and it gives us the area, negative 3 halves x squared plus 450 times x. This quadratic function, does it open up or open down? It opens down because a equals negative 3 halves. So we just need the coordinates of the vertex. A equals negative 3, b equals 450, c equals 0, although we don't need that right now. For the x coordinate of the vertex, we just need to find negative b over 2a. That's negative 450 over 2 times negative 3 halves. That's negative 450 over negative 3, which is 150. This is the optimal width, the width that maximizes the area. The area function, or the y coordinate, gives us that area. So let's see what that is. Area, if the width is 150, would be negative 3 halves times 150 squared plus 450 times 150. Well, 150 squared times negative 3 over 2 is 33,750. So that's negative 33,750. 450 times 150 is 67,500. So the area, the maximum area, is 33,750 square feet. $33,750 square feet. Let's look at the graph of this. If you graph y equals negative 3/2 x squared plus 450x. Let's pick out a good viewing window before we press the graph button. The x values represent how wide the thing should be. We've seen 100, 150 looks like the maximum value, 200. How wide could we make it before we have no area at all? I mean, we can make it 200 feet wide. Could we make it 400 feet wide? It would be 400, and then 400, and then 400, and that would be 1,200. That would be a little bit too much. 300, 300, 300, and that would use up all of the fencing material. So, and we're picking out a viewing window. I'm thinking probably 300 would be as far as we need to go. So an x min of 0, x max of 300, x scale of maybe 100. And how much area? Well, we can set the y min at 0. The maximum value is 33,750. So let's go up to 40,000. With the y scale of about 5,000. 5,000, 10,000, 15,000, 20,000, 25, 30, 35, 40. And graph it. There we go. So, if, as we did at the beginning, we make the thing 100 feet wide, like this one right here, it tells us it will enclose 30,000 square feet of area. If we pull back from that and just go 50 feet wide, the area is only 18,750 square feet. If we go large, up to 200 feet, evidently by 150, the area is 30,000. But if we want to enclose as much area as possible, we should make it 150. And the other dimension, I think, is maybe, well, what would it be? 150, 150, 150. And so it'd be, we'd have 450 feet left. Cut that in half. So I think 225. If we make it 150 by 225, it'll enclose as much area as possible. So, the dimensions of the fence of maximum area are 150 feet by 225 feet. I'm thinking maybe one more. Sample 7. Is there a C part? There is a C part. I don't know if I want to do the C part. Basically, I'm just looking for the maximum height of this arrow. Okay, it says the height of an arrow fired from the top of a building. First of all, I want to say probably not a good idea to fire an arrow from the top of a building. I don't see this ending well. So top of a hill, perhaps, where it's going to be safe wherever the thing lands. But anyway, the initial height of the arrow is 80 feet above whatever we're whatever we're going to call the ground, 80 feet. And when the arrow is fired, it's going to go up. The vertical component of the initial velocity is 120 feet per second. So initially it goes up, and then it comes down. And we want to know, how long does it take to reach its maximum height, and what is the maximum height? Well, the function here, and really I should call it maybe f of t instead of h of t, because h represents the x-coordinate of the vertex. So the function gives the height at any given time. We want to know what's the value of t that makes that as great as possible. So the vertex of this, the x-coordinate, is going to be the time, and the y-coordinate, the function value, is going to be the maximum height. So how long does it take? H equals negative b over 2a. Looks like a is negative 16 and b is 120. So negative 120 over 2 times negative 16, negative 120 over negative 32, which is 3.75. And it's seconds. It's the numbers in the domain, and the numbers in the domain of this function are seconds. Click a stopwatch as soon as the arrow is fired, and it's the number of seconds that elapse from that point in time. So 3.75 seconds into its flight, it's reached its maximum height, and it's on its way down, or it's about to be on its way down. What is the maximum height? We evaluate the function at 3.75. F of 3.75 equals negative 16 times 3.75 squared plus 120 times 3.75 plus 80, which I think ends up being a whole number. $305 feet. So the numbers that go into that are in the domain where we evaluate the function are units of time, seconds, and what comes out of the function that gives us the height. The height is indicated in feet. If we were to graph this, and I need to adjust the scale, but let's punch this in first. Negative 16, clear it. Negative 16 x squared plus 120x plus 80. Back to the viewing window. For the x-min and the x-max, we want to know about how long is the arrow going to be in the air. Well, it takes 3 3/4 seconds to reach its maximum height. About that long, maybe a little bit longer to hit the ground. So I think certainly no more than 10 seconds. So 0 to 10 should be good. How high is it going to go? Well, it reaches maximum height of 305 feet, so I think if we set the y max at about 400, we will easily cover that. So instead of 40,000, let's just go 400, just 400, and a y scale of about 100. So we look at the x scale, it's 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. The y scale, 100 feet, 200 feet, 300 feet, 400 feet. Graph it. And the height as a function of t, what do I do with the x scale? Oh. X scale should be 1. There we go. 1 second, 2 seconds, 3 seconds, 4 seconds. That's better. Okay, so its initial height, second calc value, is 80 feet. After 1 second, it reaches a height of 184 feet, still on its way up. After 2 seconds, it's reached a height of 256 feet, still on its way up. 3 seconds, slowing down, but it's reached a height of 296 feet. During the next 3/4 of a second, it goes up another 9 feet, I guess, to its maximum height of 305 feet. And then its velocity is temporarily 0 right there. At the moment it stops going up, starts going down right there. And it does so for a while, and I think we could have solved the quadratic equation to figure this out exactly, but an approximation I think is fine. About 8 seconds. The height is 16 feet. Maybe after another tenth of a second, 8.1 seconds, the height is just a couple feet above the ground, and then in no time it'll hit the ground. So about 8.1 seconds if you're looking for a short answer to problem C.